Hello. We have discussed a lot about topology optimization last week and this week, and the last lecture we also touched upon shape optimization and size optimization towards the end of last lecture using what are called wide Bezier curves. Now, let us see what one does when we encounter a practical problem where we want to design a compliant mechanism. So, we are going to discuss a case study. Later in the course we will see a lot more of these case studies to see how we can put together all the theories to some good use to solve practical problems. Today's case study is called a Cam-flexure clamp. Let us look at what that is and how we can go about designing. So, here I am going to take a paper that is that was published a long time ago 2004 in the journal Finite Elements in Analysis and Design, and to say that it is a practical problem, we have a co-author here, Dr. James Eder, who was at that time working at Kulik and Sofa Industries in Pennsylvania in the US, while I and my postdoc Lu Zhang In were at University of Pennsylvania in Philadelphia. So, this problem actually came from the industry where they want to solve a problem. I am not going to reveal actual details of what the industry's problem is, it is always trade secret for them, but because he is a co-author we have put only what the company allowed us to disclose in a publication. After the work was done, we wrote this paper where we are able to share with the rest of the world how we solved a practical problem. Clearly an industry person is involved, it is a practical problem. So, what we will do is look at that paper and try to go through it, so that we understand what the problem was, how we used topology optimization, little bit of size optimization, shape optimization, and then size optimization to solve a problem. In fact, the interesting part of this case study is that when you encounter a problem, you come up with your specifications, that is, you say I have this much area and this is where the force is going to come, this is where I want output displacement, and this is how much of stress that I can allow. So far we have not talked too much about stress, and there are a number of papers that try to deal with stress constraints or strength considerations in compliant mechanisms in the context of topology optimization or shape or size. We are not talked about all of that, but it is an important thing in practical applications, because we need to keep the components strong. In fact, at the beginning of the lecture we said the entire philosophy of compliant mechanisms goes towards creating compliant and strong design. So, strength is really important, and hence stress considerations are paramount in compliant design. Here we had such a constraint, and how much maximum stress do we allow in a compliant mechanism. You can make up all your specifications and go to the topology optimization or shape or size optimization and hope that there is a solution to your problem. But how do we know at the beginning that the shape or not the shape, the design domain that we have set for ourselves actually can give a solution? So, that was the case here when Dr. James Eder came to us, and he had already tried all his methods using finite element analysis and the design expertise that was there in Kulik and Sofa, and they had found that there was no solution, or at least they could not find. When they came, we started applying our topology optimization solutions thinking that we can solve any problem, but then there were issues, but then we got around that, and I will tell you that story. Okay. So, it is called Cam-flexure clamp, it is a name that we made up for it, and it is actually an interesting device. It is quite small actually. So, if we look at the problem specification that is over here. So, it looks like a block, it is actually quite small. Well, I have a little prototype to show. This is the optimized design. So, we should not look at the design right now. So, it is actually a device that this prototype it shows where I am looking at the actual device with the final design. So, what it is it has 3 layers as you can see. So, we have layer 1, layer 2 and layer 3. Okay. Cross section if you see, top layer and bottom layer are identical. The middle layer there is some design, that is the compliant design here. And if you look at the holes that are there in the top and bottom, they are just normal circular holes, whereas the middle layer has an elliptical hole, and I have a more like a wrench or a spanner which has actually elliptical cross section here. So, I can put here and then turn. So, that was the idea. So, I put in the middle one and turn. In the process something happens and there is a function that comes in. So, let us go back to the file now. So, we have the top layer and then bottom layer, we have top layer, bottom layer, middle one that is the clamp, okay, that clamp layer. So, that clamp layer is where we had to put our compliant mechanism in such a way that when I put this elliptical tool in here and turn the elliptical hole that is there in the middle layer and turn it by 90 degrees, then that would make this middle portion extend towards the other side, that is farther. This is the fixed one, farther from the fixed side. So, there are holes, there is a tiny hole here, tiny hole there, and those are aligned, whereas the middle one is misaligned, it is a little bit off. You need to use this elliptical tool to bring it and align with this, so that I can insert, think of this as a wire. Actually Kulikand software does wire bonding of electronic equipment, they make machinery to do wire bonding. So, think of that wire there, that wire will be put into aligned holes. Okay. For that let us actually look at the cross section here. Okay. So, whatever I talked about, the top layer, bottom layer and the clamp layer. Clamp layer is the one that we need to design, this layer. It has a misaligned hole in it. So, it is a misaligned hole and this is the elliptical hole in the center. Right now minor axis is being shown rather than major axis. When you put that elliptical tool at the top like this and then turn by 90 degrees, then this elliptical hole part of it will move this other hole which is misaligned over here. So, all the holes will be aligned like this, okay, like in the part B here. At that time you insert a tube or a wire, a cylindrical tube, right, you just insert it. Now, when you insert it, what happens is this middle layer which has been stretched towards the right, okay, cannot go back, wants to go back because elastic segment wants to go back, cannot go back. In that process it will very tightly hold this wire. It is all, this whole clamp device is to clamp this tube in place and should be very quick. This elliptical tool comes, it turns by 90 degrees, things are aligned, tube comes in and then you remove the elliptical tool, it is held. Now, the misaligned holes are aligned and it holds. So, if you think from the compliant mechanism viewpoint, here are the specifications. In fact, they had very strict design domain specifications. All the units here are in inches because this is United States where this work was done. So, all are inches. So, the height of this is 0.05 inches, as you can see here, the height from here is 0.05 inches, and they said that you cannot go outside this blue region. That is all their company had restriction in the machine. It is a complicated machine in which this is a small part, they wanted to make it with metal actually. So, compliant as we said at the beginning also is not just for plastics, it is for any material. So, here they wanted to do with metal, in particular they were actually thinking of making with titanium because that has good strength and good low enough Young's modulus. So, it is a small part, so they can afford to do it in titanium. So, there is a hole here, elliptical hole that we see the dotted line in which that elliptical tool is put to turn it. So, it is a complicated actuation, it is not like our usual here is a force, there is a displacement type of thing. It is the whole ellipse that is like this had to be turned 90 degrees. So, finite element analysis is also quite tricky. So, now we have to do topology optimization to see what should be the distribution of material inside this. They did not have any volume constraint. They said that as long as you do not go outside this region, that is 0.05 inches, all others are there. No, for example, this is 0.025 inches, same thing here, this is 0.028, this half, another half. So, all the things, all the dimensions are here. So, if you were to fill this whole thing, we are taking only symmetric top half here. So, looking at the top view, this ellipse will be completed, this hexagon will be completed and so forth. Okay. Now, the idea here is that the misalignment that we see between these two, the larger it is, the better for them. Why is it better? If it is large misalignment, when apply a force and align it, when it tries to go back, if you think of the middle clamp layer as a spring, we are moving the spring by a large displacement. If there is some spring constant k, it will not be uniform, let us assume that is a constant spring constant, k times the delta, how much misalignment you have covered, k times delta will be the force with which the tube will be held. When misaligned holes will insert the tube, much like this pen, when it wants to go back, now the tool is removed and it will try to hold, the middle layer will hold it very tightly. So, there is a requirement for maximum output displacement. When the input is given for this elliptical tool, when it turns this elliptical hole, you want this point, okay, where the hole is, that point, you want it to move a lot towards right in this figure, towards right side we want to move a lot. So, that we will get a large force of clamping. Okay. That sounds good. I mean, you would have already tried before coming to us, that if you put the whole entire material and make it move a lot, right, and you get a lot of clamping force, but then when you take a structure and move it by a large displacement, the stresses are going to be very high. So, that is where it was a problem. So, he had put 120 KSI, that is 120 kilopascals as the limit of the stress, with all the consideration they have, titanium material, whatever their factor of safety was, they said do not exceed the stress of 120 KSI. Okay. And the force of clamping, they wanted certain force value as well. So, you want to have so much clamping force, at the same time stress should not exceed a particular value, and highly restricted design domain. If you fill that whole thing and try to move it here, and there is a little hole here that aligns, and he had found that the stress will be so much high when you want certain clamping force. So, misalignment, if you keep it very low, your stress will be low, but you do not have enough clamping force. So, here is again a compliant mechanism design problem where there is output displacement is needed, that is a flexibility one. In this case, misaligning the misaligned hole, aligning it, you need to move this hole from here to align with this top and holes in the top and bottom layer, that is a displacement or compliance requirement, and then the clamping force is the stiffness requirement. That is what he came up with. So, when that problem came, so we thought that we will put it through our topology optimization, and then we thought we will refine it later with size optimization. So, first we went to topology optimization, put down, and then it was not easy. So, we tried to first see how the problem is, we looked at it some intuitive design. So, where we thought that okay, let us put material everywhere, that he had tried, but we had to do it ourselves. Industry would have tried, but we wanted to do. Again, this is an ellipse, it is not a circle, because the elliptical tool is the one that turns it to move to the right here. We put material everywhere, and the stress in that was 1 mega psi, okay, that is 8.83 times the 120 KSI that they had put a limit. So, clearly putting material everywhere, it gives you 8 times stress. So, what do you do? Where do you put a hole? So, you have now there is no volume constraint in this problem, okay, this is a small part, okay. You fill the whole thing with material, and if you try to satisfy the clamping force requirement, then you have a lot of stress, 8 times the stress, almost order of magnitude more. So, then we thought okay, intuitively let us make a hole, not topology optimization, just initially just remove some material, there is a beam there, there is a beam here, okay, curved beam, let us see what happens. Then we were able to reduce the stress to 350 ksi, but in the process the clamping force was also reduced because it became flexible. So, by making flexible we made it strong, because when you flexibly when you do it is flexible spring, you do not get much force there, and the stress somehow was gotten down to 350, but still farther from 120 ksi that is allowed. So, intuitive whatever you try it does not work. So, this is one of those cases simple, here is the force, there is a displacement type of thing people may be able to solve intuitively, but presented a practical problem one needs design methods. In fact, some of us who work in compliant mechanism area think that people do not use compliant mechanisms even though they have many advantage, because there are no accessible design methods. So, now many people have worked, we have a lot of design methods, that is what we are discussing in this course. So, now we tried something else, made it very flexible, then stress reduced to 213, still twice as much of 120 case that we want, clamping force dropped down to 2.4 pounds. So, it is not a good thing. So, by arbitrarily trying this and that we do not get anywhere here, which is what James Eder had told us when we began the work, but we did it for ourselves and all that we described in the paper, so one can understand. Then we went to topology design. So, here we are maximizing the RO is a reaction force, that is a clamping force, UO is the output displacement of that hole which is misaligned and we have to align it. That displacement of that towards the right is our one objective function. Other objective function is to make the clamping force as large as possible. Design variable the same old indicator function rho, and then equilibrium equations for the load case 1, load case 2, and some constraints on stress. For the stage 1 when you are applying the force, second when you remove it, then it is going to relax a little bit, there is going to be another stress. In both cases we wanted to put a stress constraint. We actually put material volume constraint because that is one way we can actually make the algorithm stick to certain amount of material, even though practical problem did not have a material volume constraint. So, this problem when we tried the usual topology optimization, there is a hole or not there, we put that, and we also put non-design domain. INSYN actually allows non-design domain as well. At this time INSYN was there, but we had to write our own code. So, here because the elliptical tool goes there, all along this elliptical hole we put some material for sure, that algorithm cannot remove that material, we put that and solve the problem, minimize negative or the product of output displacement and reaction force, clamping force. These are all the constraints, and these are the stress constraint, volume constraint, equilibrium constraints, all the optimization thing that would have. We can take gradients and all that is possible here. We take penalty parameter of 3 for that rho which we discussed in the last lectures, used E0 which are titanium's properties, and we got a solution like this. Like any other topology problem we get this. Again we have these one node hinges, point flexures, edge flexures, all the usual things, and we have this, some things are there. Now we went and looked at the result that we got. We did not really get low enough stress or enough clamping force. Then we had to make some tweaks to the thing, they are in the paper, you can look them up, and we got something that is not even well designed. For example, we removed this design domain. Why should it be complete circle? We thought even if it is partial we can still put the elliptical tool. Then it started giving disjointed ill converged regions with different type of stress constraints that we had put, right. So, looking at all, when we finally look at that, somewhat of a design that is kind of close we got, where there are different segments, and this elliptical hole we have not shown here, but that is there, we have to connect it. Okay. And another one, so these two are actually inspired by these, they are not actually. So, look at, if you look at this one and this one, you do not find any resemblance, somewhat of a closeness. Here the algorithm had lot of doubt, and we also tried to show that doubt. In fact, when we are looking at all this topology solution that we got by varying parameters, removing stress constraints, adding them and looking at all, gave us the idea that what we should really worry about here is what is important, is it bending of the segments or axial deformation. If you think of axial deformation, axial stiffness is quite high for a beam segment, right. There we get to serve the clamping force. If it is bending, the stress is limited and we can try to satisfy the stress constraint. So, finally, we thought, after whatever we have learned from topology optimization, we did not get close to the 120 KSI and the clamping force of 100 pounds or whatever. Instead, we went for analytical design. So, where we try to look at, for the design that we have, if I just take any of that thing that topology optimization gave, it is telling us that there should be some beams, right. So, we thought that the beams may be more like this. Let us take a V beam one, there is one segment here, another segment. Now, let us see what should be the height of this, what should be this span of this edge, this H and D, and some width of this these two beam segments, and we try to plot the axial stress, bending stress and the total stress. How do they vary? If you see axial stress based on the displacement that we have from beginning to later for this V beam thing, that actually reduces, whereas bending stress increases and reduces, and there is a peak, of course, when you add them up, there is a total stress blue curve, there is a peak. So, by looking at analytical expressions of the reaction force, by this what I mean is that this V beam thing, we apply a force when this elliptical thing is put and it is moved to the right, how much displacement it goes, what is the stress in that case, and when you release it, we know how much reaction force will be there. So, we can calculate all that analytically here, we put those and try to come up with these two variables D and H, what should be the ideal ratio. When we did that, something interesting happened. So, we thought, we showed that when you have the elliptical hole here, when you take a beam like this, okay, from here to here, a single beam, no matter what width it is, it does not serve the original requirements that they have, right. So, we thought that, okay, how about using the stress, each one of them has a particular width here, that is the size optimization, and the height of this, compared to the span of this, how high it can be, they are all different here, even the span is changing. So, there is a notion of shape change here. Topology, we believe that it was suggested by topology optimization. In fact, it was, because we tried intuitive a lot of them, we did not get anywhere. Topology at least gave us that how it should be connected, and then we thought, if there is one beam here and one beam here, the V beam if I take, for the stress limit that we have 120 KSI, how much reaction force does it get here? We computed that, that was nowhere close to what we wanted. Then we thought that we should take more and more of them, because then the reaction force gets added up, each one of them goes to that 120 KSI limit. In a way, each V beam here had to have a different span L here and the D height there. So, we got all of them and they all move like this, these are rigid portions, that is a nice rectangle here and here. We put them, several of them, and then showed that whatever original size that they had, we proved to them that it is not possible, you have to add a few more, and that was a revelation, because as a designer, like at the beginning we had started with the space which was all given like this, but it turned out that the beam segments you put, how many beam segments you pack into this area, we are not getting enough force. So, here the force is 30 pounds that they wanted, the force originally, and the clamping was a little more than that. So, whatever beam segment we get were not enough. So, we want to extend the region a little bit. When we did that step by adding these things one at a time. So, we went to this, we were able to achieve it. So, here it was maximum of 120 150 ksi, clamping force was 50. By adding a few more we were able to finally achieve what we wanted. So, now you see several beam elements like that, and we had to go a little bit more than the original space that they had, and finally it was made. This elliptical tool that you have, it is a 3D printed model, but this was to be made in titanium, where we have the displacement. When I put this elliptical tool here and then turn it, when I turn it by applying force, it is like this, but turn it 90 degrees, that will make the middle portion go a little bit. Now, we can put a wire through this aligned hole. So, there are summary conclusions that you can see. Finally, it was able to meet the specifications of the clamping force and within the stress, but with a larger size. That is the key. So, when we start the problem, we cannot say this is my design domain, get a compliant mechanism for that. For what you are asking, that space that you have may or may not have a solution. So, if the algorithm does not give you a solution, it could be that there is no solution. So, how do we know ahead of time? So far in the last 2 weeks we have discussed this structure optimization inspired methods for compliant mechanisms. Before that for a week and before that one more week, we had used how we can use rigid body linkages and come up with design methods. So, we have in a way talked about 2 classes of methods. One are come from one extreme of rigid body linkages. So, where we use rigid body model, linkage synthesis. The other extreme of stiff structures, where we use structure optimization methods, topology, shape and size. We took one case study, then we realized that all the methods that we have are not readily applicable here. We had to make some changes, as you saw in this case study. So, next few weeks we will discuss a few more classes of methods, not just these 2 classes. We have a few more methods have emerged in the last decade or 12-14 years. So, let us look at those in the coming weeks. In the next week we are going to discuss a method that uses a different model for capturing the kinematics and elasticity of compliant mechanisms and make it more like a selection based method. So, we will see, and after that we will have few more methods that we can discuss, so that we would have several categories of methods. Hopefully, one of them will be useful for solving a practical problem, which is always the ultimate goal for any design method development research. Thank you.